So I'm J.P. Nicot. I'm a research scientist with the Bureau of Economic Geology. My area of expertise is water resources, in particular groundwater. And I've started looking at water use in the oil and gas industry, I guess in 2006, and I've been following the industry since then, in terms of water use. So I'm going to present a few results of my study. Here is the same type of information you may have seen just a few minutes ago with Bill showing the water use in the state in terms of use, consumption. Actually, just a comment. We haven't made much. We haven't done a lot of discussion about use and consumption today, but I think it's important. But I'll pass also that topic today. And what I'm going to do, I'm focusing on the mining sector. Thank you. I'm focusing here on the mining water use in here. So I did two surveys. Let's just one in 2011, and I look at the water used by the industry in a mining sector in general, and that mostly oil and gas and also aggregates. So a good number to remember is about 200,000 acre-feet in the industry, about 60% by the oil and gas in fracking, a little bit drilling, but also water flood. I'm talking fresh water here in the Permian Basin. So I'm going to give a bit more detail about that information. So it is a map showing a bunch of wells, tens of thousands of wells in here. Those wells have been fracked with what I call high volume hydraulic fracturing, using more than 1 million gallons of water per well. So, and you may recognize some of those names, the Eagle Ford, the Barnett, Haynesville, and there are many more, especially in the Permian Basin. So, so you've seen the location of those formations being fracked by the industry, and here is how much water they use at that time. It was more than 80,000 acre-feet for the whole state. And now I think there are over 100,000 acre-feet of water being used, not consumed, used. And that information is not readily available. I get it through a private vendor called IHS, whose main activity is to collect information. So that amount of water, as I said earlier, it's a small fraction of the total amount of water used in the state. But when you start looking at the county level, the picture is a bit different. I find that those plots I'm going to show are very interesting. On the y-axis, on the x-axis in here, you have the county population in log scale, and on the y-axis, you have the amount of water used for all uses in the county used for fracking. And the size of the bubble is the absolute amount of water used by the county. Tarrant County in here uses about 8,000 acre-feet of water a year for fracking, so large bubble. Those counties a lot less, smaller bubble. And the interesting trend, clearly, is that the less population in the county, the higher the fraction. And we see that for the Barnett Shale, we see the same thing for the Eagle Ford, and the same thing in general for the Permian Basin. And so Loving County, with a very low population count, most of the water used in the county is for fracking, but the population is tiny. And if you look at the size of the bubble, it's much smaller than this one. So a lot more water used in Hector County than in Loving County, but a lot more water used for fracking in Loving County. So you have to keep those numbers in perspective when you look at fracking. So, but in any case, we still want to limit the amount of freshwater used by the industry. So in addition to conservation and other technical advances, we can use brackish water, or we can recycle or reuse the water. the problem of, not the problem, but one of the issue to look at when you use brackish water is to understand the resource itself, which is not very clearly understood at this point. You know, we know there is brackish water. We know there is probably a lot of brackish water, but we don't know exactly what would be the impact of using the brackish water and how much we can truly use. And on top of that, it may it may compete with municipal use too. And it's more expensive because typically you have to go deeper to get the brackish water, and the well yields are not as good. And reuse recycling is also something important to do, but and I'll show you numbers. You can recycle only what comes back. You know, if there is no flow back, well, there is not much to recycle. And the big problem of the industry right now is basically the matching between where the flowback happens versus where water is needed. So a huge logistical issue. So let's look at these two topics a bit more in more details. Here is a map of produced 10 years ago, but still basically the latest about that topic, showing the brackish water in the state. So, and the cycles represent the different places I mentioned earlier, Eagle Ford, the different places in the Permian Basin, the Barnett, and the yellow color means like you have some brackish water, and the density is not truly related to the amount of brackish water. It's more like the number of sample points. But so some areas do have a lot of brackish water, and some have only brackish water, like in the far west Texas or in South Texas in here. So in the context of the studies I've done, also talking to industry people, I also collected information about how much recycling do you typically do, and how much brackish water are you using? So in 2011, here are the numbers. They probably have changed a little bit. Probably a little bit more brackish water being used, a little bit more recycling being done, but I don't think not by a lot. So some places basically don't show any recycling, or very little. Like the Eagle Ford, basically all the flowback goes into injection wells, and that's also true for the Haynesville. Although the Haynesville now is not very active, but at the time it was. In the Permian Basin also not very much recycling. The highest recycling is in the Anadarko Basin, the Granite Wash in here, because the flowback is typically relatively less saline than elsewhere, maybe 20 to 30,000 acre-feet ppm. I mean, so it's easier to use. In terms of use, the use of brackish water in some areas is fairly high, like in the Permian Basin, for the reason like there is not anything else to use. So the industry can use brackish water when it's needed, and hopefully that would translate into areas like the eastern side of the state, where they could also do the same thing, use more brackish water. Let's talk a bit about the recycling now. So I've just going to show a few headlines in here. More recycling in here according to that headline. And growing recycling in Texas in here. But then you have also headlines like this. Well, companies don't do recyclings, and service companies are disappointed, because they don't want to do recycling because it's so cheap to do injections. So there is kind of that. It's not clear exactly what's happening. I think there is some recycling happening, but a lot less than what could be done. And just a few more slides showing the amount of water flowing back. As I said, you cannot recycle more than what flows back. And so the percentage in here represent how much of what you injected has flowed back after 1 year. And for shales, it's typically you know, in the low 20s, 30%, but in tight formation is a lot more than that. And here is a plot showing that information in more detail. It's the Barnett Shale, the time scale on the y-axis, on the x-axis, on the y-axis shows how much flows back compared to what you injected. So 100% means you recover the exact amount that you injected. So if you injected 5 million gallons, you produce 5 million gallons. It is clear that the quality of the water is totally different, but in terms of volume, it's about the same. So that's the Barnett, so relatively large flow back that you would be able to recycle, although initially it's fairly low. You know, it's the amount of water being used by the industry for recycle, it's no more than 10%. And for the Eagle Ford, you have similar number, except that the average value in here is about 40%, not 100%. And the Haynesville is even lower. On the Marcellus in the northeast is even lower. So with those points, you know, I hope that I introduce the material you'll be interested in, and I'll be happy to answer questions in the discussion.
Defer to the end of the
Yeah, exactly. Yeah.
All right, thank you. So what I'd like to talk about this afternoon is the sort of the other end of the prior presentation. This is more about the treatment of the frac flowback and produced water. So initially, I'd like to start with just a quick, and we've covered off on quite a bit of this, but the global market regulatory drivers. And if you look at this, this is a global look at all water. The mega trends being climate change, population growth, and we've heard quite a bit about those. But also we look at unconventional oil and gas in there. It's looking to be a game changer, especially in North America, beginning in Europe, South America. So we're looking at the water consumption and usage as part of the mega trends globally. But when you go down to the bottom and really start looking at what the industry needs are, from this, it's really reuse efficiency, resource recovery, alternative sources of water, which we'll cover off a little bit. But those three things are really applicable to what's going on in this market. But first, let's look at what the historical practice is. Within this space, it's important to understand when people talk about the cost of water, the companies, the exploration production companies, are not looking at what it costs to, for example, turn on the tap and get a gallon of water. They're looking at their life cycle water management costs. And that's an all-in cost that includes finding and sourcing the water, transporting the water. Then they have to store the water on site or near where the hydraulic fracture is going to occur. And then they blend that water with the sand, the proppant, and the less than 1% of the chemistry. They do the frac job. The water flows back, and again, the percentage of water that flows back is going to vary based on where you are in the country. They have to collect that brine, store the brine, transport the brine, and then dispose of the brine. And historically, that practice of disposing the brine is disposal wells. So that represents the historical practice. When we start looking at reuse, that changes a little bit in that they still have to source the water. However, now, for example, if you get 30% of the water back from the prior well, you now blend that with 70% fresh water, 30% flowback or reuse water, and now that makes up your water. So you've cut your water consumption of potable or brackish water source by about 30%. Then you blend that water, transport, and again go through the same process, transport the brine. And then if you take it a step further, so that's a reuse scenario where you're taking that water, treating it, and reusing it in field. If you take that a step further and you look at recycling the water, Again, the same process occurs. However, now you're doing some sort of desalination of that water, and you're actually recycling it and getting beneficial reuse products out of it. So now you can treat it for discharge. You can get NIPD's permits, for example. You have beneficial reuse products, i.e., we've demonstrated you can make road salt from frac water, produced water. You can make calcium chloride flakes, all kinds of beneficial stuff in that produced water. Or you can reuse it in the field for an additional frac job, or even 10-pound brine. So there's all kinds of uses for that water. So what are the drivers? Why would a company look at reusing, recycling water? First and foremost, regulatory. Second is the economic. And third, it's sustainable to their drilling operations or their drilling plan long term. So from a regulatory perspective, this is a survey that we did. It's not a scientific survey by any means, but more just conversations with the E&P companies. Their big concerns are getting the water, sourcing the water. There is concern growing about seismic activity, and that's generally associated with saltwater disposal wells, storage and transportation of the produced water, and then also how they treat that water, both the flowback and produced water. Those are the issues that they look at and see as there's risk associated with all those to their business model going forward. So if we look at the economic side of it, the first part of it is sourcing the water. And these numbers are in barrels, so 42 gallons per barrel. But generally they're paying somewhere between 20 and 90 cents per barrel of water. And when you compare that to what we pay at the tap, that's considerably more. Second is transporting that water historically has been done via truck, right? So, anybody that's been in Cleburne, Texas and sat around there and seen all the water trucks going through town have seen these. And then they get it to site, they store it, they transport it again. Again, it's $85 to $110 an hour. And then disposal, anywhere from 25 cents on the low end is if the company owns the disposal well, $4.50 on the high end if it's a commercial disposal well. The next phase, if you add in recycle or reuse to that, they go through what they call a primary treatment, and you're really just treating that water for total spent solids, oil and grease, and they'll pay anywhere from $1.50 to $6 per barrel. And then going further, desalinization, you add on top of that $1.50 to $6 per barrel, $1.50 to $3 per barrel for advanced desalinization treatment, and then go a step further to zero liquid discharge. You're at an additional $1.50 or $1.53. So all in, you're starting to get into the $10, $15 per barrel range to go to zero liquid discharge on this water. From a sustainable point, the relative part of this slide is this is the amount of water that they would acquire without any reuse scenario, and this is the amount of water that flows back and would have to be disposed of. So in an active field, they use this much water and they have to dispose of this much water. And then as the field matures, what this graph represents, we're not drilling anymore. So now I have no need for new water, but I still have this produced water. And that has to go to disposal. The second scenario is if I use fresh water for fracturing, again, now I've reduced the amount of fresh water I have to acquire. I'm still reusing all this water, but this is what I would refer to as the tipping point, and the thing that we need to recognize in water use is there's all this produced water. At some point, this produced water here has to be accounted for. And this water right now is all going down disposal or for treatment, and this water, this produced water, will be going forever. So if we look at one state that really, I think, is held up there as the highest reuse capability in the country right now, it's Pennsylvania. And so in Pennsylvania, they reuse somewhere or recycle somewhere in the vicinity of 89% of their water. So what's the difference between what's going on there and the numbers that we just saw that are happening in Texas? Number one, there's data. There's very good data available in Pennsylvania from the DEP website. Every company has to self-report where all their water goes. The second one, it's purely economic. They do not have easy access to disposal wells. There's somewhere in the vicinity of 7 disposal wells in Pennsylvania and 750 in Texas. Big difference. It's an economic driver. And then the other one is regulation. They also passed regulation about discharge levels. They can't take frac water, produced water, to municipal treatment plants anymore. So big incentive to reuse water. So in summary, I guess a couple of takeaways. Number one, the technology is available today to treat this water, whether it's flowback or produced. It exists. However, it's more expensive than going to a disposal well. Secondly, technology companies are creating newer or next evolution technology to reduce that cost. That will then bring the cost of treatment more in line with what today is the acceptable disposal cost. Third, each project is unique. The water in the Eagle Ford is very different than the water in the Permian, very different than the water in the Barnett. The technical solution in each of those geographies will be different, and it's a challenging water. When you look at, for example, seawater, in comparison, that is very easy to treat, right? Seawater has roughly 32,000 parts per million dissolved solids. The Permian water is about 4 times that. Eagle Ford's about equal to that. Barnett is about 2 times that. So when you start looking at salinity, that's one big issue. The organic content, the dissolved, emulsified, and free oils that come back, as well as the suspended solids in this water, needs to be accounted for. It's an evolving market. More technology is being developed daily, and I guess there is no single silver bullet that can do everything in this market. It doesn't exist. There's a lot of claims to that, but it's not there. Thanks.
Hello, everyone. If we're staying awake enough, we'll see if we can do it better here. Keep everybody awake. So it's a pleasure to be here. I thank TAMEST and Danny for inviting me to speak. There are several people here at University of Texas that can talk intelligently on this sort of energy and water space, in particular to oil and gas and power generation. So it's glad that I was chosen to talk to you today. It'll probably be a little less technical to try to relate it to the theme of economics and water of the conference. So we'll go through a few slides here and some of my perspectives. This slide is just a basic summary of the power generation breakdown in Texas, actually shown for ERCOT, which is roughly the same as for Texas, and how much of the water is used for cooling water, right? So it's somewhere between 400 and 500,000 acre-feet per year is consumed basically through the cooling towers and forced evaporation from cooling ponds associated with power plants in Texas. As Bill showed earlier, this is about 4% or so of total water consumption in Texas. So we can look at this on one hand and say, well, that's a small number, so why should we think about power generation and water consumption? Is that a big deal or not? And I'll talk about that during this presentation. In the breakdown there, right, so we're over 9%, and we'll be slightly higher increasing percentages of total generation will come from wind now with the CREZ line, so that's a zero, essentially zero consumption technology in terms of water. The water consumption comes from cooling off steam cycles in power plants, effectively, right? So I have a steam cycle, I need water to cool off as part of that cycle. So nuclear power plants tend to be a little bit higher water consumptive than coal-fired power plants, slightly higher than these natural gas combined cycle power plants, which there are an abundance of in Texas. There's also 2 dry-cooled combined cycle power plants in Texas. So if you ask anybody, are there any power plants in Texas that use dry cooling, which is essentially having a big car radiator outside of your power plant? There are 2 combined cycle facilities that do this in Texas, and so it's some people believe that's the trend. Combined cycle power plants also are a trend towards lower water consuming power plant technologies, because usually about 2/3 of the power generation comes from the gas turbines part of the cycle, and that's not a steam cycle. So the cooling load on the gas turbine part of a combined cycle power plant is low, or pretty close to zero. So that's why natural gas looks low when you think about combined cycle power plants. When you think about where is the water consumed in Texas, this is a breakdown of water basins in Texas. The outline there is for ERCOT, the bold outline, but the darker the color, the more water consumption per year. No surprise, it's mostly in the east where most of the power plants are, because that's where most of the water is. So if you want a reliable source of water to fill up your cooling pond, to be associated with your cooling tower or in your cooling system, then East Texas is more of the place to be than West Texas. And so those in West Texas have to rely more on groundwater, those in East Texas more on surface water. So if the water use or the water consumption appears low, then nobody cares about water consumption at power plants, right? Well, apparently it can become a concern. So in the Brazos River Basin, this story is about the Brazos River Basin and sort of the ongoing water disputes there about the water use for agriculture versus cities and power plants, right? And it stems from the story in 2011 when water rights were getting called in the Brazos River Basin, and they're going down the list, and eventually they get to cities and power plants, and the decision at the time from the TCEQ was to not cut off access to water for power plants. And I have highlighted here, so a lot of what you would see in the literature or the explanations from TCEQ was a relation to public health and safety. So you certainly want electricity to keep things like the municipal water supplies pressurized so that you can use fire hydrants to put out fires or something like that. That sounds like a safety issue. Electricity for hospitals that don't have their own power generation on site. So we can think about many public and health safety issues where we'd like plenty of power generation or the water supplied on a sea level. The quote here from the farmer is like, yeah, I know cities and people need water and power plants need water, but we're farmers and we were supposed to be higher on the list in terms of water consumption, in terms of priorities and the water rights priorities as they are. So if you have a plan and then the drought comes and they don't use the plan, then it sort of makes you wonder what's the plan for, right? And if we think about power generation, if you think about how much electricity do you need for health and safety, if this is the reason to not follow the water rights, then what is public health and safety from an electricity standpoint? Do I need full peak power demand in the summer so that everybody can have air conditioner? It's about 60, I think 2011 was maybe 68 gigawatts of peak power demand in ERCOT, and maybe 75 gigawatts total. Do I just need it to meet air conditioning loads for people? If it's hot in houses, that can become a health issue. That can be a public health and safety issue. Do I need to make sure enabled city services are available, like I said, such as making sure fire hydrants and the water supply is pressurized to put out fires? Or do I need to make sure commercial buildings are operating? Is it public health and safety to make sure Best Buy is open on Saturday or on Friday? Is it public health and safety to make sure I can produce petrochemical products from industrial facilities? Is it public health and safety to need agriculture? Well, we can maybe answer that one. They took, suspended water rights for agriculture, so maybe that wasn't seen as so much of a public health and safety issue. But the question is, maybe is the decision basically come down to economics? Where do you use the water, and what is the economic gain from consuming that water in each sector? Agriculture is generally lower than the industrial sectors, just in terms of the value-added products that are made per the unit of water that's consumed in the process. So maybe $2,000 an acre feet of value for every water consumed in Texas for agriculture. And if we think about just wholesale electricity sales in ERCOT, if we're thinking about cutting access to water for power generation per se, then the value is an order of magnitude higher. So right? We definitely place a high value on being able to consume electricity. We get many services from this, and we pay for these services. So in some sense, if you charge more for water for power generation, you could probably pass through the costs. People will still want power generation for air conditioning, for example, in the hot summer. So was this an intervention in the ERCOT market? So there's a lot of discussion in the electricity markets of, well, it's Texas, free market, with like low regulation, we're open for business, et cetera, et cetera. And so you're like, well, do we have a free market? So in here, if the state of Texas owns the water resources and lets people access them according to their will, then if you have basically said, well, I'm not going to cut off legal water access, at least, not physical water access is different, but if I'm going to not have legal water access cut off to power plants, is this an intervention in what is trying to approximate a free market or an open market for power generation? Especially if I think about if I'm a new power generator and I want to build a new particularly thermal power plant in Texas, do I need to install dry cooling because if I can't get access to surface water? Or can I install a wet cooling system and think that the state of Texas has got my back if there's a drought and they're not going to cut off water to me? Is it different if I built my power plant in 1970 versus if I built my power plant in 2014? This is a good question, right? It can essentially change the economic and dynamics of the ERCOT market to some degree and may be seen as a uncompetitive issue or preferring legacy generators over potential new generator. A lot of the new generation, again, is low water consumptive technologies anyway, from wind, solar, and natural gas combined cycle. So the good news is most of the new things people are investing in are inherently low water due to the economics of those investments. So do we have a plan for this? Again, if you have a drought plan and the drought comes and you need to put it into effect, then and you don't use it, then we'd say, okay, maybe we need to come up with another plan. How does power generation come into that? It may or may not have to be a part of that plan. It's not to say that water is not a good use in power generation. That's a bad use or consumptive use of water. It's a good consumptive use of water. It plays a good role. It makes the power plants more efficient. Are there technologies to use that don't consume as much water in power plants? Yes, there are. Do people change from using an existing power plant that uses and consumes water using a cooling tower or some other design system to one that uses a dry cooling system? There's not much precedent for that. There's precedent from going from one wet cooling system to another, usually due to environmental thermal issues and sometimes economic issues. But there's not a lot of precedent for changing from a wet cooling system to a dry cooling system because the economics are tough and the power plants are designed, and it actually is from an engineering standpoint, is difficult. But if you wanted to install a new power plant with dry cooling, well, then you can do that if the costs of water to you are somewhere in the neighborhood of $3 to $6 for every 1,000 gallons, which is roughly $1,000 to $2,000 an acre foot. At these prices, you start to weigh the trade-offs of the capital investment for dry cooling versus the water costs, operational costs. So it can happen. So what are some options to deal with issues like going on in the Brazos Basin if a water needs to be cut off from agricultural sector? Places like Australia create, more open water markets. I guess in Texas you can trade water, but it's not necessarily open to the public what's happening. So it could be a small water market, it could be temporary leasing, it could be things to basically compensate or help compensate, not necessarily only agriculture, but any water user that might want to lease his water rights during a drought. So these kinds of things can help. Is this, the canary in the coal mine, or is it chicken little to talk about water running out and power plants and needing water for power generation, and this is creating conflicts in how we've governed water? I think, from a long-term perspective, you can recognize that fossil fuels is essentially taking us away or enabled our economic activity to be fairly decoupled from the environment, right? I'm not dependent upon rain flows so much if I'm going to pump groundwater using electricity to irrigate my crops. I don't need rain-fed crops if I'm going to pump for agriculture, and I'm going to create new industrial type of products, petrochemical products from oil and petroleum that substitute for biomass that we would have otherwise been trying to make plastic cups out of before. So fossil fuels have coupled us to that. As we get more going back towards having the land or the flows of nature, if you will, sunlight, wind, rain, being a part of their economy, then we can expect to have more of our economy exposed to these flows, and I think this is just a natural consideration. So again, thermal power plants can operate without water. It's not the most economic thing to do, but if you're water scarce in a region, you can do it. One of Australia's latest coal-fired power plants was a super high pressure, high temperature, what they call supercritical coal-fired power plant that uses dry cooling in a hot environment, and it has higher efficiency than all the other coal plants on the grid. So if you build a new one and use the latest technology, you can have a high-efficiency dry-cooled power plant. I'm going to end with this slide here, which is attempting to sort of put this in a really sort of broad context. This is the percentage of essentially household income in the United States spent on food services and energy services, just data from the Bureau of Economic Analysis. So the bottom line is green, which is energy. The red line is food, which is decreased from essentially the end of World War II all the way until 2006. And then a slightly increased to then. So ever since 2006, the average consumer in the United States is spending slightly more of their income on food. And since 2002, the average consumer in the U.S. is spending a higher amount on their income on energy. And when you put these two things together, we're spending a higher amount on our food and energy expenditures since 2002. So what's not in here is the play of water, right? If we think the energy-water nexus, or the agriculture and water, are going to become more important in the future, then we can think, well, water is going to be more embedded in these costs in the future. And if I think water is going to be the new oil, probably means somebody's going to price it, because oil is the largest traded commodity in the world and flows around the world. We're not going to ship huge tankers of water around the world, probably. But if we're going to put a price on water and we're going to internalize the cost of water more, then those are going to get passed on, certainly through the food sector and also probably through the energy sector to some degree. So another pressure that makes these costs rise higher, basically thwarting a 60-year trend that created the middle class in the United States after World War II, right? So food prices got cheaper for 60 years, and now that trend has basically stopped. So with that, I'll end that happy note. I'll end with this, a plug for a book. Now, it's not a super plug because I get $0.00 if you buy it. But I did edited a book for ASME Press on the context of thermal power plant cooling. So it has perspectives from the environment, perspectives on economics, and perspectives on the engineering side of how power plants operate, why they consume water, and how to calculate and understand how much water they consume. So this is by ASME Press, and it's available online. So I thank you, and we'll look forward to the discussion. Thanks.
Welcome, I'm Tim Finley from the Dow Chemical Company. I appreciate the opportunity to come here and talk. I'm going to talk today about water conservation in the context of the petrochemical industry, but I'd really like to start by asking a couple questions. What I find is that in the world of water, there's often very strong misperceptions, even among those who have strong knowledge in the space. And so I guess I'd like, by show of hands, to understand who here really views the water issue in Texas to be a West Texas issue, or more strongly a West Texas issue. Okay, that's good. How about the question of, there's been a lot of dialogue today around trading between municipal and ag. And so I've actually bumped into in my career a number of times where people have this strong opinion that it's really just an economic trade-off. We're going to solve our municipal water plan by putting in place water trading programs, and we're going to get reallocation of ag water, and more or less the balance is going to work out. Is that view here in the room? Okay. I see a few hands here. Okay, so I'm going to step through a presentation on water management on the Brazos. I'll say for the Dow Chemical Company, it was a very emotional event, because I think we came to appreciate really over the last few years, and maybe even to an extended decade, that the world in Texas has truly changed. We've been on a run of about 40 years, I think, of pretty strong rainfall flows in many of our basins, specifically from Austin kind of west. And we've seen now, I think, in the last 5 to 7 years that that's changed. I'm really proud of the fact that in 2011, 2012, Dow got recognized for a Texas Environmental Excellence Award for our efforts in water conservation. And so as I step through our slides today, we'll talk about that a little bit as well. A little bit about our site. We're at the mouth of the Brazos River. We are the largest petrochemical company in the Western Hemisphere, our largest site. We represent about 65 production plants on about 5,000 acres with about 8,000 direct employees. We estimate that there's about 10 jobs for every direct job on site. So, our impact on employment in Texas is significant. The impact of this site to our company is also significant. We produce about 32 billion pounds of products a year, roughly 40% of what we produce in the U.S. and 20% of what we produce globally. We have fence line partners kind of in the area, different industries that set up and use our products. We also supply water to all the local municipal users. In here in red, I have a comment that was actually made by a colleague of mine at another chemical plant. And in the heart of the drought in 2011, we were talking about how much water we had left to continue to run. And his comment was, okay, well, we're kind of in a bad way. We're down to about the last 100 days. But we're not in a situation where if we shut off, we impact the U.S. economy. And certainly this site, if it were to shut off production, it would impact the U.S. economy, because we're such a supplier of raw materials to other manufacturers in the U.S. that there ends up being a ripple effect. And certainly I think as we think about water management in the state, we have to think about that for a number of these coastal facilities, including the area on the Ship Canal and in Texas City, where they are a huge producer of materials that we need for manufacturing in the U.S. A little bit about on our water. We actually take water off the Brazos River. Our location was created in about 1940 or so, and at that time the leaders recognized the need for water, and so we ended up getting water rights on the Brazos, relatively senior, but certainly not the most senior. We've got a couple of small local reservoirs that store roughly 45 days worth of water. And when those reservoirs don't have water, we've gone to relying on BRA for interruptible water, and or we've got some residual long-term contract water with them. But clearly when the river gets low, we're in a precarious spot. One thing worth noting is that the water demand down here in the lower Brazos is about 100,000 gallons a minute. And so it is a big supply. I'll say roughly 8% of the water supply that comes out of the Brazos. To me, the picture kind of on the top of this slide is impressive. This is the flow in the largest river in Texas in June of 2009. And this is at a location almost immediately upstream of our intake. And so one of the things I present to folks is that usage, pumping, reservoirs, capture, can dry out really any river in the state, is my opinion. And when we're kind of in the mode of actually managing flows, these rivers are basically glorified drainage ditches, right? People can turn on pumps and they can shut the water off, they can turn them off and turn the water back on. The second slide down here below is a picture of where we were in drought in 2011 across the state. And in 2011, for 6 months, the only flow that was coming down the Brazos was water that was bought by Dow, GCWA, and NRG from BRA to meet our supply needs. In the absence of that flow, the river wouldn't have flowed. When we got into the fall of 2011, in discussions with BRA, it became very, very concerning what was going to be happening the next year. We came through a year where temperatures, evaporation were higher. The rates at which their reservoirs depleted were higher than expected. And really the message was out there was we'd be hard-pressed to get through another year. They concluded that they didn't really have any excess storage because they were worried about supplying kind of their real firm contracts. And we're predicting that 2012 that was like 2011 would have them at 30% by kind of into the next summer. When you take a look at water supply, Ben Franklin had the comment that you'll know the price of water when the well grows dry. Is certainly, I think, a statement for any user, right? We all have what we need water for. And quite honestly, everybody who's talked today has a valuable use. The thing of it is that when you get down to that point where you realize there's very little water left, you start to appreciate what you need to do. And so, let me back up one slide here. For us, it was really the key understanding that water is essential and that conservation really needs to be thought of differently than we'd ever thought of it in the past. We need to think about conservation or doing conservation as a means of generating new water, right? Whatever the most expensive water is you can imagine, that's the value you should place on conservation. And by doing that, you can create water for additional future use. And so we kind of went on a path of addressing a number of issues, kind of advocacy. We went about trying to secure spot water, which makes it clear that there's really no trading mechanism. When you go shopping for water in the middle of a drought, nobody's got any. Because in the Brazos Basin, you're trying to buy water from municipal power and ag. From municipal power and industry, because all the ags don't have it anymore. That reallocation that we talk about with ag water happened in the Brazos Basin in the 1980s. And so if there's ag users out there, for the most part, they're junior, and they're already off. And so, we've got an objective of trying to increase long-term storage, and that's just kind of a basic need. We've gone about trying to do internal conservation. We did about 10% in 2011, about 10% in 2012. And, we certainly are concerned about kind of the multi-decade strategy going forward. Couple things here, we really increased, one of the key things I think was that we had to change the financial motivation. We had to go from seeing it as an incremental cost to really a risk management issue. And so that really drove our change in mode. Couple things, when you get down to the very practical level, you got to dig into the details with water. And so we had to go through 5,000 acres of plants and really quantify what everybody was using water for, what all the piping and infrastructure was doing, how many leaks were there. We brought in big users and did reviews and set about a list of projects that we thought we could actually accomplish. This is kind of what it looked like in a practical form. Basically we went through every project, both supply and demand side that we got identified, and try and put it in the price of water. And so when it comes to actually solving problems, you need a quiver or an arsenal, right? You want everything that you can imagine there and try and put it on a cost basis, and then kind of work through that and pick the ones that you can accomplish when you need to and as cost effectively as you need to. When we went about doing this, we set up probably 8 or 10 different teams focused on different aspects of executing projects. And there were 6 or 7 individual plant teams that end up executing those conservation projects. The result of it was roughly 16,000 gallons a minute, or 25 MGD worth of water conservation. That included everything from simple recycles to we took about 3,000 gallons a minute of municipal reuse water from our city wastewater plant. As we look at kind of stress going forward, the Brazos, roughly, I'll say 4 months and every 3 years is going to go through an episode where there's very, very low flows in the summer months. And we see that. We see deterioration of kind of base flows in the Colorado and above PK, and it gives us great cause for concern that we need more storage, we need conservation, and again, we need lots of measures to improve this. This compared to a backdrop where, based on the bottoms here in red, we only had a couple events in the 90s, but we've got almost half a decade now of events in the recent years where we're having problems. So what's the outlook? In 2014, we've been close to initiating water rights calls already. There is some flow in the water or in the river at the moment. Rainfall, unfortunately, has primarily been near the coast. And so the Brazos Basin reservoirs aren't refilling, kind of like the Colorado. And so again, we step forward with cause for concern. Again, I talk a little bit about kind of there needing to be lots of solutions, and here's kind of my list of solutions, starting from simple things like transfer all the way to evaporation to recover condensate. Certainly the ones in blue are ones where we also provide internal technologies, and so if you're one of those areas, come talk to us. One point I guess I'd like to make today is one of Texas's, I think, big challenges with respect to water is that in many of our basins, 80% of the time we have water in excess. And so that creates a perception that we don't have an issue. For many, many people, I fight it all the time. The reality of it is we go through 4 or 5 years where we have water in extreme shortage, and if we don't plan for those events, the economic damage can be incredible. Again, this facility that I support produces something on the order of $15 billion a year worth of revenue, something close to all of irrigated ag in the state. And so again, shutting off these kind of facilities has huge economic consequence for the state and onward to the country. We need to think about storage reserves. We need to think about water masters. We've been a huge proponent of that, not specifically because it benefits us, and it may a little bit, but I'll tell you it won't solve our problem. We're an advocate for it because it creates transparency. It helps people understand where water is being used, where it's needed, and it is the backdrop for creating water trading. When we make water rights calls, ag users get cut off, and at the moment there's no compensation. With a water master, I believe that you start to use the hierarchy of law, and then you create a mechanism where there's room for compensation for those who have rights who are trading them with people who need the water more. Risk mitigation. I mean, for industry, that's the key. We really need 100% reliable water, different than I think some, and we need to be working for how to assure that if we want to keep bringing jobs and industry to Texas. And then from a conservation standpoint, the mantra that I like to put out there is that as we work to conserve, the job that you create could be yours or it could be somebody you know. Could be in the ag industry, could be in gas and power, could be in the petrochemical industry. But it takes water to create jobs, and so we need to work together. And so I guess I'd like to end by just commenting that I thought Laura Hoffman made a very nice talk about we need to escalate the discussion, and we need to think about not just how to help our own cause, about how collectively we can solve broader problems for the state of Texas. And with that, I'll say thank you.
So, questions, discussion?
One of the questions I've had is, when we talk about brackish water for municipal use, we're generally talking about water at a depth of about 3,000 feet and a salt content or brackish content of less than 10,000 parts per million. In some of the discussions, a comment was made that, the mineral content is above that of seawater. Help me understand the difference between that. What are you talking about? And at the same time, as a follow-up to that, what are some of the impediments, strictly from a product standpoint, using the water with the brackish creation process itself? What is the impediment in terms of the mixture of the brackish water versus clean water with the chemicals that are used in fracking?
Okay. I think two questions. One is the difference between the produced water salinity versus a brackish aquifer. First, that water is typically, the well depth is much deeper and different formations than the aquifer, the brackish aquifers are at. And just an example, in the Permian, their average total dissolved solids, or the salt content, is roughly 120,000 versus, I think you referenced, less than 10,000. So that's the average salt content in the Permian. The Barnett's probably around 90,000. So just from a salt content perspective, that's the difference there. On the constituents that are challenging for treatment, number one is just the salinity. Salinity requires different technologies. At the lower salinity, seawater range, you can use a membrane system. You start getting higher than that, you're into membrane distillation, thermal distillation type systems, and/or crystallizers, which are much more energy intensive and expensive to operate than your traditional membrane system for brackish aquifer water. So the cost is much higher due to salinity. But also you have the organic content with that water that's produced water, whether it's produced flowback or produced water. Generally you'll have some level of free oil, emulsified oil and dissolved or and volatiles. That is, and pre-treatment is required to take those oil and greases out. In addition, you're going to have to get rid of total suspended solids, and the suspended solids are very high. And so additional filtration and technology is needed to treat that. So hopefully that answered the question.
Yeah, I wouldn't mind taking a crack at that kind of in the context of more municipal supply issue. And so there's been a lot of dialogue around brackish groundwater in Texas. And there, I think, often folks think of groundwaters that have lower salinity than seawater. And so seawater is about 30,000 parts. Oftentimes, groundwaters that have roughly 10,000 parts, or roughly 1/3 the salt, and I think are much shallower, are what people are targeting for brackish groundwater. In terms of projects, it means that it takes less energy or pressure to push it through a membrane. And often when you're pumping from the ground, it's already comes pretty pre-filtered on solids. And so by comparison, a brackish desal plant may be able to produce water for 250 to, I'll say 350, 1,000 gallons in a moderate scale, where a seawater plant might be more like $5 to $6.50 1,000 gallons in a moderate scale. And again, it's the difference between produced water then that has 10 times that much salt.
Let me follow up on something with Todd. You showed a figure that showed $3 a barrel for a desalination reverse osmosis, which is quite low if you were talking about the 100,000 milligram per liter, and perhaps it's not even appropriate, I guess, for that level of salinity. So what was the assumption in that figure?
Right. If it's a membrane system, reverse osmosis membrane system wouldn't be applicable for that type of salt content. So typically you look at a seawater RO system, for example, as being applicable up to 30,000. Some people would say up to 45,000 total dissolved solids. But the other thing that's key when you're looking at it in the produced water market, it's the recovery that you get off the system. So it's, you know, the operating cost and the volume of water you're treating is one thing. It's how much water is coming out as distillate and or permeate versus concentrate that has to go back down the well. So you're probably better off operating actually a higher operating cost and a higher recovery, because now you have less water to dispose of as well. And then, you know, when you get to those costs were additive, right? So if you look at that 1 to 3, that number, that was not including the pre-treatment, that will also be required. So you've got to make sure, it's important to understand that the pre-treatment is always required when you're looking at produced water for the membrane system and or higher distillation system.
Yeah, I was mostly concerned it might give the wrong impression. It would almost imply that, well, gee, why aren't we desalinating all of that? And I suspect that it's a little more expensive than what that figure would suggest.
Yeah, good point.
Okay.
Thanks, everyone. My name is Jordan Fernandes. I'm with Intera. I've spent a lot of time studying the Colorado Basin and the Brazos River Basin, and this question is really directed to Tim Finley. So in the Colorado and Brazos, you have large water users at the downstream end of the basin, and in the Colorado and the Brazos, again, we're seeing the lakes are emptying upstream in the basin. Now, the LCRA is building a reservoir downstream to sort of mitigate that issue, and currently Dow has 2 reservoirs downstream. Do you know, if at all, why Allen's Creek Reservoir is not being built in the Brazos Basin to help mitigate the water supply problems throughout the basin?
You know, and I'll say I'm not kind of at the center of that. I'll say I have looked into, you know, trying to source water at Allen's Creek. Allen's Creek, I think, is an interesting and valuable project in the Brazos Basin that needs to happen. The challenges, I think, really are that there's divided ownership in both the water rights and the project. BRA has a 30% interest in that project, and the city of Houston a 70% interest. You know, and so getting the parties to the position of being ready to move forward with it is one thing that's impeding it going forward. You know, a second challenging issue is Allen's Creek sits on a 7,000 acre plot of land that has, you know, 1,400 acres of wetlands in the property. You know, and so even when you reach the point that all the parties are ready to develop it, input I have is that it's, you know, could take 8 to 10 years to get through the permitting process.
Is it a reservoir that Dow is actively looking at to possibly take over some of Houston's share?
I'll say, you know, not take over. I would say that we would have an interest in buying water out of Allen's Creek if it were developed and available, as would I think others in the lower Brazos Basin. You know, certainly GCWA, and I can't speak for them, but the demand is there. What I understand is there's significant unmet demand for water in the Brazos Basin. That's been there for some time and really waiting on a project to be developed that could satisfy the need.
Thank you.
I had 2 questions. The first one, basically, I think what's been mentioned over the course of the talks is that about 25% of water is used for generating power, and I was wondering what percentage of water use is power dependent. That's a slightly different question. I don't know if there's anyone who can specifically answer that question.
Well, I guess quantity of water, we would say consumed versus withdrawal. The quantity of water consumed is single-digit percentages, estimated at 4% of all water consumption, roughly, in Texas, and it's kind of national number as well, is what's consumed for power generation and water.
Okay, 4% versus 25%.
45 is withdrawal, so if I just talk about how much water I pull from a reservoir and then put it back as hot water, then it steps up to 45% of withdrawals of all water in the U.S. So the numbers, the order of magnitude of withdrawals is 2 times higher than consumption, so it's just a different scale of number. So water withdrawals is high, but water consumption is low.
Yeah.
Right. So
okay.
in terms of what leaves the basin.
The second question is, I don't know if I saw these numbers right, but 12 cents a barrel is what it costs to take it out, about, and $3 a barrel was one example of what was given for recycling the water. Is that right? For recycled water?
No, I think I mean, typically the cost to recycle, again, is going to depend on the level of treatment. If you're recycling for reuse, so you don't need to desalinate, you know, that was in the $1 to $6 barrel range, I believe. And then if you're going to desalination, then it's additive to that is the $1 to $3 per barrel.
Okay, and versus 12 cents for just extraction, was that number correct?
I'm trying to think of where that. I'm not sure. I remember where
that was. It was at the very beginning, I think.
Yeah,
I may be wrong. Okay, so it's about a 25-time factor difference between recycled water and water that's not recycled in the price of water. I was wondering if each of you could comment, like maybe one line, as to the single most important thing that you can think of that would reduce that difference, like a contribution, an idea that would reduce the difference in price between water that is just extracted versus water that's recycled.
Right. I mean, the question is what single, you know, if you can name one thing would bring that price more in line to encourage reuse? Is that, you know, ultimately we have to work towards getting the effective cost of the technology and the operating cost down, right? We got to bring the cost of reuse and recycle more in line with what the cost of water is going to be, or, you know, that from a technology perspective.
Yeah, I would say from a, well, I don't know if I'll give a, I don't know what to flip an answer. You could raise the price of the acquiring water, makes it closer to the price of recycling. So one is to raise the low price, the other one's try to lower the high price. So which one do you think is possible? As far as the energy cost, I mean, I guess traditionally the desalination, particularly through reverse osmosis, the high cost was associated with the energy to pump the water through the membranes. But I think now the technology has gotten to a point where, I mean, it used to be maybe it's 1/10 the cost of energy than it was 10 or so years ago, and it's getting pretty close to the sort of theoretical minimum. So I think the costs now are really starting to get dominant on the capital cost and not the energy operating costs now. So it's really a lot coming down to the actual materials and capital and paying back the engineers for designing it. So,
excuse me. In terms of the question I asked earlier, I certainly understand the difference between the, you know, the 100,000 plus parts per million water versus the 10,000. Part of that question was, or intended to be, you know, what are the economics of using the water at the lower levels, 3,000, 4,000 feet, that are in that 10,000 range, 10,000 parts per million range, as opposed to, you know, to use it as opposed to using the water that, you know, that's at the fracking depth.
Okay, so what is the impact on hydraulic fracturing of using a brackish, more brackish
Instead
water?
of using fresh water,
Right.
why can't you use that brackish water? And what is the impact of that brackish water at the lower level, salt level, you know, on the chemicals that are used in the fracking process?
Yeah. That's a good point in that they've, you know, what happened in the Marcellus when the cost of disposal got really high is by the very creativity of the industry, they started developing higher salinity chemical packages for fracturing. So nowadays, you know, they've moved away from a pure slick water frac to gel-based fracs. They've reduced water volume that way, but they've also enabled the higher use of higher salinity waters, you know, so you can use that saline aquifer for fracturing. What you have to look at is the scaling tendency of that water. It's the sulfate level, the borates, and some other specific constituents. But absent those being an issue, you can use that. And then the other thing I would suggest is if you're going to do inland desal, you know, you can look at using the concentrate off of that system also for hydraulic fracturing.
And I guess the other part of that is, do you see a tendency to move in that direction as opposed to using fresh water?
Yeah, I think companies definitely are moving that direction. Again, the things are, number one, making sure you get rid of the total spent solids and making sure that water is right. But the salinity, they are looking at that. There is for the guy doing the frac job, there's a slightly higher cost for using saline water, but it's not a huge difference, but there is a higher cost associated with it. But they are moving that way. I think Pennsylvania went that way in a quick way because of the cost. Other areas of the country are moving more gradually that way.
Thank you.
I like to add too that extracting brackish water is more expensive. Wells are typically deeper and have lower yield, and also it's more expensive to transport brackish water or to move it around. You know, you have to be more careful about your water lines because you cannot afford a leak. You know, now you are contaminating the aquifer. You have to be more careful with your storage ponds and all those things. So all this has a cost too. You know, so and you have to spend more time in the office designing the frac itself. You know, what type of additives too. So you know, all that has a cost. So so that's basically the reason why they would use fresh water than anything else.
Let me just add a comment as well to this, because I think we're mixing up apples and oranges in all these conversations. When you're talking about using water that has some salinity in it, like the flowback water, the water you put in the reservoir now is coming back at you, and you're going to use that in the next frac job, then when you look at the economics, one of the things you have to look at is the transportation cost, and there's a big transportation cost in the economics. You can't just look at what it costs. Not only that is, if you're going to use it again, if you're going to use the flowback water, you don't normally desalinate it. So the cost to desalinate is not necessary. That's not there either. So I think maybe the lady who asked the question before got a wrong impression from the answer than what it is. I think that the answer is that we're using more and more of the flowback water in additional fracs, but then we still have the problem that Todd pointed out. Eventually, we're going to stop fracking, and we're just going to produce, and there will be some small amount of produced water that we will produce that will have to be disposed of. You can dispose of it in disposal wells, or you can go through and treat it and use it for drinking water. I mean, there's water that's being produced in a heavy oil reservoir in California that after it is treated, it goes in the aquifer that feeds the city of Monterey's water supply. So do we have the technology to do that? Yes, it's just money. And we don't want to spend too much money on that if we can avoid it. It'll always be cheaper to re-inject the produced water than to treat it and desalinate it so that it can be used for drinking water.
I also like to add that typically they blend the water from different sources. Like when you say recycle or reuse, you know, maybe they use 10% or 20% of that, and the rest of it is basically fresh water. So it's not like they take, you know, flow back and inject it in the next well. You know, they blend it.
And there are some non-technical things that would drive people to not reuse water, including lease contracts, where a lease owner might actually ask for them to drill a groundwater well on their site and only use their groundwater because they could charge them for that too. So sort of a good neighbor, talk to your neighbors, and if they want to conserve, then have them want to use reused water or recycled water as much as is possible.
Well, another comment?
No, I would say yes. I mean, he's not joking. You know, this is what's happening. Yeah.
I didn't think
Not joking. All right.
No, but